So, put this here. Hello? You hear me? Yeah? It's okay? Not okay? Hello? Yeah. So, we will continue our journey into population biology. And now it's time to talk about interactions. As I told you yesterday at the end of the first lecture, it's obvious that if you go out in nature, you see that species somehow interact, influence. One species can influence the other species. So there are interactions which are quite widespread in nature, and we want to take this into account so that we can study multi-species dynamics. Okay? Well, so we have studied single species, and the next kind of obvious step is to study two species, pairwise interaction. Okay? So two, and this is obviously probably you know that that's open the way. Then if you have pairwise interactions, so I have two species, then you can think I have species A interact with species B, but B interacts with C and D, and so on, and then you get a network of interactions. Okay, that's if you put ecology and network on Google, you will find an enormous amount of things. And that's a whole subject in ecology, in ecological networks. So, but what we want is to start with this kind of basic piece, which is the two species interactions. Okay? Before we start, let me just mention that this is not the only way to proceed. There's something which is called higher order interactions. Higher order interactions are interactions that are not pairwise. They are interactions, say, that only takes place when you have, say, three. Okay, it would be a third order interaction. You have A, B, and C. It's not just adding A with B and B with C. It's something that happens only when you have the tree. Okay? So this is called higher order interactions. We won't study higher order interactions here, but it's good for you to know that what we are doing, which is pairwise interactions, two species, and from two species you can go for many species, that is not the only possible way to study interactions between species. In this higher order interactions is actually a hot topic now. It got published in very highly cited journals and so on, and there's a lot of work. It's more like still at a very theoretical thing. Okay, but if you go for look for higher order interactions in ecology, you don't get a bunch of papers, but you get some papers that are very interesting. Okay. So, okay. We will study pairwise interactions. Okay, so we will put this presentation on online on the summer school website. So I won't follow exactly all the words that are presented here. Okay. Anyhow, so we will begin with two species, but before going to really writing down some equations and studying some models and so on, there's a preliminary question, which is, what is an interaction? Okay. Well, most of people, when you say an interaction, they say, okay, interaction is like something that most probably I can see, like, so to make a kind of a simple example, of like Animal Planet example, like a lion eating a zebra, okay, something it's obviously interacting, okay, and you see animals fighting or something. All of this can be interactions. But I want to remind you that we are studying population ecology, population dynamics. And we want to describe things at the level of populations. So there are actually two meanings for the name, for the word interaction. One is related to the mechanism of interactions. And the other one is related to the effect of those interactions at the basic level of individuals on the population sizes. And if you remember well, our basic ingredient to build everything that I've built in the first lecture and we will do in the summer course is population size. So from the point of view of population biology, defining interactions is something like there's an interaction between species A and B if the species A population level of species A changes the population level of species B, and vice versa eventually. Okay? So this is the definition that we will take. Why I'm insisting on that? Because you can have, because if you say now, I will use this definition, how species A influences species B at the population level, I can now make a classification of interactions. Okay? So how would it be this kind of classifications? Okay? So say species A, species B. And let's say that the interaction is such that the population, in presence of B, the population of A increases. So I put a plus here, okay? And the population B, let's say it decreases. So I will call this predation. But let me emphasize, predation is usually from the point of view of individuals, a very specific interaction where one individual kills another from another species and consumes it. Yeah? So, but under this same name, plus minus, you can have different mechanisms, not only the direct consumption. And the prototypical example is host parasitoids. So you have usually an insect or something. You have a host, and you have a parasitoid that goes and usually lays the eggs inside the host. The eggs will grow and actually kill the host, and then will emerge the new and the offspring of the parasitoid. So this is not always called predation in the most strictly sense, but it goes under the same name here because we are looking at things at the population level, not at the mechanisms that actually are in action. Okay, so here you have different biological phenomena going under the same name because we are just looking at interactions as acting at population levels. So you can have different mechanisms. Okay? So, well, you can say also that you can make a table here. You can have minus, minus, plus, plus. Minus, minus will be called competition. And this will be called mutualism. And actually, you could have something like minus 0 and plus 0 and minus 0. And this has some names that I forgot. It's Commensalism and Amensalism. I will come to it. Okay. Yeah, okay. Commensalism is this one. And this is amensalism. But we won't study this here, okay? An example of commensalism would be like a species, say a big animal that can transport some small species. So it's not affected by the small species, but the small species get the benefit because it is being transported. Okay. So using this idea that interactions are at population levels, at the description of interactions only at the populational level, you get the classification. Okay, and in this summer school, we will study this too here. Maybe there are mutualism in your projects, okay? But from the point of view of population dynamics for two species, mutualism is usually not so interesting. It's more or less trivial. Everybody benefits and so on. Okay, population increases, gets to a carrying capacity, and that's it. And we want to focus today on this predation. Okay? So our task in this lecture is to study predation. Right? Predation is a nice interaction. So it's actually something that you can see. Yeah? It's a direct interaction. You have a predator and you have a prey. I'm saying this because competition will be different. Okay? Competition sometimes is they have species A and species B, and they have no contact. They just compete for food, for nutrients. So it's indirect. It's mediated by the resources. So it's not a direct interaction. But predation is usually, predation or host parasitoids are usually direct interaction that you can go and take a photo or something. Okay? So something that is very, very basic to the description of interactions. And we want to have a mathematical description of the population dynamics of a system consisting of one predator and one prey. That's the basic thing we want. And this will take us to the famous Lotka and Volterra model. And we will now build this model. You can read a little bit about the lives of Lotka and Volterra. If you go on the web page, you can search a little bit interesting people. Like Volterra is a mathematician, was a mathematician, a very famous mathematician actually. He is known for the theory of integral equations, which is a very important topic in mathematics. And well, this was one contribution he made to mathematical biology. I mean, avant la lettre, in the sense that this name didn't even exist, mathematical biology, at the time of Volterra. And Lotka is very curious. This guy an American that was born, I think, in Russia or Ukraine, actually. and studied physics initially under a guy that physicists know, which is a guy called Poynting, from the Poynting vector. Physicists will say, okay, Poynting vector. And then studied chemical physics with a very famous person, Ostwald. Ostwald is maybe the last important scientist who didn't believe at the beginning at the atomic theory of matter. Yeah? And he was, I mean, he's very important in studying kinetics of reactions and so on. And the idea of Lotka was, well, instead of having chemical reactions, your populations are not chemical elements, but if these populations are actually populations of animals or something, can't we do the same thing for biological systems that we do for chemical systems? And that's how emerged the ideas of Lotka about mathematical biology. So we will need two functions, and we will say the function n is the number of predators, and the function v goes for victims, is prey predation. So what we want is something like, we want to write something like that. Okay? And we have to make some assumptions. Okay. Our model will be as good as our assumptions. Okay? That's very basic for modeling. Okay? So we will assume that this prey, in the absence of predators, can grow exponentially. Okay? This is the simplest hypothesis we can do. Obviously, you could say, oh, maybe it's better to put logistic. Okay, we will do this later. Okay? But this means that I'm actually assuming that the population is limited only by the presence of the predator. There's no other limitation. Okay? And then you will say, in the presence of the predator, I will have a new term with a negative sign. So if you think that here I wrote A times V, A is all constants, all parameters are supposed to be positive here, okay? A is the intrinsic growth ratio of the prey in the absence of the predator. And you can say, okay, when the predator appears, it's like, okay, that A goes to A minus something, some B times the number of predators. Okay? That is the easiest thing I can do. I say the intrinsic growth ratio just gets smaller due to the presence of the predators. Okay? You will say, okay, what is A and B? Well, A and B are constants here. This is the intrinsic growth ratio. That's the measure of the balance of birth and death rates. And well, this here will be called like an attack ratio. Okay, how the predator affects the population of the prey. So if you do this, when you end up with something like A minus B. Okay. So now, just for people that are not so much acquainted with Yes, I'm using n. Oh, okay, n. What did I do here? Let me see. Okay, okay, it will be easier. Okay, I'm consistent with p. Okay, the n was not the. Okay, forget about the n. put a P. Okay, that was a typo in the first, but it's consistent in the equations with P. Okay. Yeah. Thank you. So, okay, so for people that are not so much acquainted with the differential equations, we want to have two equations for two variables, for two functions, okay? A solution is a pair of functions, P and N, okay? You want both of them, okay? So you need two equations, okay? It's called a system of ordinary differential equations. And now I need an equation for P, okay? So I may have to make assumptions. So for the time being, I've made two assumptions that the prey grows exponentially in the absence of the predator, and that the predator affects the growth rate of the prey linearly. Okay, it's a linear function. So if you put just like A here, and you'd have the growth rate going down due to the presence of the predators. And now I have to make similar assumptions for the predator. So the predator, what we will say, this predator is a specialist. In the absence of the prey, it just dies. It needs the prey. So it's opposed to the generalist. Generalist is a predator that can prey upon different species. This makes things more complicated, point of view of mathematics here. And well, anyhow, what we are doing is this is the prey is essential for the predator. So it's a specialized predator. There's no option for him. So we will say that, okay, this is the death rate. Now, in the presence of the prey, the predator gets benefits. Okay? So let's say that the death rate will decrease. Okay? So you can take, let me just see what layers I'm using. That the death rate goes like D goes to G minus some C times V, which will give you here at the end, okay, will give you this P times CV minus D, okay? And this is the system of equations called the Lotka-Volterra system of equations. Okay? Two equations, two unknowns. It's well formulated. In order to obtain solutions, we have to give initial conditions. Okay? And once we give initial conditions, meaning that the value of P and the value of V at a given initial point of time, initial instant, the solution is well behaved and is unique, exists, and it's a unique and mathematically beautiful thing. There's no complications. And moreover, it's possible to show that this system, if you give the initial conditions positive, the solutions will remain positive. And this is kind of a rule of thumb for all mathematical models in population biology. If you are doing your group work and so on, and you get something that has a negative population, it's probably wrong, okay? It's really something that should not happen. I've never seen anything good with negative populations, okay? You see a model that, once I saw a seminar, a person gave a seminar on, it wasn't epidemiology or something, and so the person had to hear this, the basic model, but the basic model has a problem. It has negative populations. And then I will modify this in order to enforce more positive things. Obviously, it was a mess, okay? So you better have, from the very beginning, be sure that all your models have positive populations, okay, positive or, I mean, can also be 0, okay, so larger or equal 0. Non-negative. Well, good. So, and there's this dictum. It's pretty much like physicists do mathematical modeling, is we have the equations, we want the solutions, okay? Which is not usually what people from math know here. It's not usually seen as a so interesting thing for mathematics. Mathematics is usually concerned with the equation as an object per se, and studying the mathematical properties and showing general results about the equations. But what we want is, we want solutions, and that's it. But the story goes, as almost always, that this equation, the system of equations, does not have a solution in terms of known functions. Okay? And I repeat what I told you yesterday, this is no problem, actually. It's just that it's not a mathematical problem in the sense that, well, known function is something that's it's connected to your knowledge, not to a mathematical structure. So it has solutions, but we cannot write them in terms of something we already know, like sine or logarithm, exponential, inverse trigonometric functions, or hyperbolic functions. No way of writing down the solutions of this equation. Okay? And so, what should we do in face of this problem? Because we still want to have informations about what this model predicts. We want the predictions. Okay? Good. Well, nice equation that don't have the two ways, and one way is numerical integration. Who has never heard about, I mean, I told you about numerical integration, the word yesterday, but before that, who has never heard about numerical integration? Raise your hands if you don't know what's numerical integration. One, okay, some of the, okay, it's easier because people are usually shy. It's easier to ask, who knows what numerical integration is? Okay, most of you know what's numerical integration, but, well, there will be a class today at 6 about what is numerical integration, but it's a way to compute the solutions and find the solutions, but not as a known function, but as a table of values. Okay, a function can be given as a table of values if you want. Okay, if time, you get time 0, you have a value. Time 0.1, you have a value. Time 0.2, you have a value. So give you a table of values, enormous tables, with millions of points. You can do this, which is called the numerical integration. You get this table, and then say, okay, well, I have to work with a table. No, you plot, okay? At the end of the day, you got a plot, and that's fine, okay? So, but I won't do this here, because this is what people call a little bit like brute force things, okay? Pow. And numerical integration is something which, you know, I'm saying numerical, means that you have to give the values of A, B, C, and D. But then you say, okay, what values? Because this depends on the specific system I'm working. Then I say, okay, I will give arbitrary values, and then you get a table, and then get the plot. But this is only valid for this value. Okay? And then you have to make this like, okay, if I change the values of A, B, C, and D, will it really change much of the solution, and so on? Okay, more on that at the evening session. What we will do is to proceed with a qualitative analysis. So a qualitative analysis is trying to figure out how the solutions V and P look like without actually writing down the solutions, neither as a table nor as a function. But maybe we can get a lot of information just by knowing the general form of P and V. So in order to do that, for the Lotka-Volterra equations, just by the way, tomorrow we'll do also qualitative analysis for computation, which will be different from the Lotka-Volterra type of qualitative analysis. Okay, here's a little piece of mathematics I have to write down. If you are not mathematically skilled, okay, just forget. You can catch up at the end of the calculation. Okay. So I have two equations. Okay. What can I do with the two equations? In this case, I can do something which is very, very weird. I can divide one equation to the other. Just do the second divided by the first. So I take, okay, this one here, which would be dp dt, and I divide by dv dt. And then I cancel that. Okay, you will be saying, this guy is completely weird. This works, okay, actually. And, well, there's a formal mathematical reason it works, okay? So I'm not doing something which is, I mean, this is just to make the thing simple. I don't want to prove theorems about the smoothness of the functions and that they have inverse functions, all of this, because they have, actually, that somebody showed this, and I'm just using a bunch of mathematical results that lay behind this, that gives me the say, authorization to do this kind of thing. So, okay, so what do I get? Well, the P is P, C minus G. CV. Okay, CV minus D divided by V A minus BP. So, and now magic happens, because, you know, in this kind of things, it's nice when magic happens. That you don't need to go and really use strong numerical things and so on. Magic happens, and you can say that this implies that dp divided by p, you put here, and multiplied by A minus BP is equal to GV, goes here, times CV minus D, and divided by V. Okay? Here, everything depends on P, and here, everything depends on V. Okay? I can integrate both sides, and I can do this integral. And the magic is I can do it. Because you'd say, if I have a more generalized thing here, maybe I could do the same. And you could try to do the same, but it actually won't work because it's only in a simple case that it works. So if you have this, then you have this integral will give you log A times logarithm of P minus B times P is equal to G. There's C first. This time to C times times V minus G logarithm of V plus an arbitrary constant of integration, which I will call H. Okay? And now, well, I can resemble this in the following way, just for convenience. CV plus BP minus G logarithm of V minus A logarithm of P equal to H. Okay? Okay, this would be minus, but okay, it's not important. What is the D? CV minus D. I'm putting everything on this side and then putting the H here. So minus logarithm of P. Okay? It's a constant. Okay? Now, people that have not followed the calculation, it's now time to come back to the, okay, you forget your Facebook things, and you can now catch up. I have done a piece of manipulating the equations, and I came up with an expression that says that I don't know P and V, which are functions of time, okay? They're functions of time. The solutions have to be functions of time, okay? But whatever solutions I have, they have to obey this relation, because this follows from the equations. And this relation has something very, very interesting. There's no derivative anymore. No derivative. It's not a differential equation. It's a relation between P and V. There's no differential equation anymore. There's no derivative of V in P. So this says that if I have solutions V and P, which I don't know, but if they are solutions to the Lotka-Volterra equations, they have to obey these relations. Okay? Good. And what can I do with these relations? I can do a very nice thing. I can now say I have a relation between P and V, has to obey this. There's an arbitrary constant. Oh, okay, so you say arbitrary constant. You don't like arbitrary things, okay? This is determined by the initial values. If you give the initial value of V and of P, then you give a value here, 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 then you get your arbitrary constant is not arbitrary anymore. It's just, it's dependent on the initial conditions. So, let me just erase the calculation. And now, once I have this relation, so why I'm so excited about that, because it's not a differential equation anymore, I somehow integrated the equations. I can now draw a plot, and one axis will be P, and the other axis will be V. And then I can say, okay, I can draw, okay, this is just, let me just say what I used at, okay, so it's V here and P. Then I say I start with initial values of P and V as a point here, okay? Now, which determines my arbitrary constant. And now I want to know, over the time, the geometric locus of this relation. Where do, in the PV plane, where do lie the points that satisfy this relation? Right? And then what you get, well, this you have to do. You do it, well, it's possible to do it more or less by hand, but it's just a case of plotting. You go for any plot program. I mean, I think even with Wolfram Alpha, thing like that, will do it for you. Just write plot, and will give you the points that satisfy this relation in the PV plane, and it will be something like that. So I have a nice picture. So this is for certain value of H, okay? For certain initial conditions, then you say what happens to if I have other initial conditions. Say I started here, actually get also something like that here, and here you have, here you have the general aspect of the curves that describe the solutions. Okay? So that is to say, I don't know V and I don't know P, but if I start with a certain initial condition, I will be constrained to stay on a certain line. These lines are called trajectories. Okay? Actually, what will happen if you start here, you will go this way around here and here. Okay? You could ask why not the other way around? Then you have to do some extra calculations. Okay? So that's what people call a phase portrait, and this is called the phase space of the equation. Okay? And you have the trajectories or orbits, depends on your background, more mathematical or more physics. So you still say, okay. No. Just there's one point. First, I have not made any assumptions here besides the biological assumptions that were in the equations, which is exponential growth in the absence of the predator, of the prey, linear relationships about the growth and death rates, and generalist, specialist predator. That's the assumption. I wrote down the equation, and this is just the result of the calculations. Now we will go for the interpretation, and then to the critique, which will have to do with what you are saying. Okay? I will come back to the going out of the orbit thing. Okay? So, but first, what's the interpretation? Say. We'll do more or less the same thing. Yeah, just the same. It's a matter of. What you could have asked also is if I had more complicated expressions here. Okay. So maybe depends on how complicated. Maybe you could still have some separation, like getting integrals. But what would happen is usually that the integrals you cannot do the integrals. You cannot find the integrals. And then, well, it's not worth doing the thing. And anyhow, so, but what does it mean to have a closed curve, right? All trajectories are closed. Trajectories which are closed mean they start here, they go on for some period, and they come back exactly to the same point they were before, which means I have a population of a certain number of prey and a certain number of predator. After a certain period of time, I will get back to the exact number of prey and predators I had at the beginning. Okay? So that's a periodic solution. Okay? And it has a typical time to go over one cycle, which is called the period. And the period depends on which cycle you are. Means the period depends on the initial condition. Okay? So if I'm here, say because I started here with a certain population here, I go on, I will have a periodic solution, and then I will have a certain time associated for the time to go over one period here. Okay? That's the period solution. The period depends on the initial condition, depends on the trajectory here. Here, if you end of thing. Now, I say periodic, but we have something else associated to this, which is oscillations. Periodic oscillations. Periodic oscillations I think I have a better plot here. Okay, look at that plot here. Say you begin at point 1, okay? From point 1, which is something like here, to point 2, what happened? The number of prey increased, and the number of predator also, because the number of prey is the projection to this here, so it increased, and the number of prey is the projection here, it also increased. Okay? Now, when you go to point, say, let's go directly for point 4. No, okay, point 3. Still, you have increase of prey, increase of predator. But beyond the point 3, I have decrease of prey and increase of predators. And I go on, then I have still increase in predators, decrease of prey, then I have still point 6, increase of predator, but, you know, a smaller amount of increase, yeah? Slowing down. Increasing, but slowing down. And decrease of prey, when you go to 7, decrease of predator and decrease of prey. Then you go to 8, you see that, well, there's still decrease in the number of predators. The prey is almost unchanged, but when you go back to, you go for the point 9, then you have increase of prey and decrease of predators, and then at point 1, still a small decrease in predators and an increase of prey. So this is going up and down, okay? So the solution, if you want a plot of the solution, say in time, you want to P, for instance, it has to do something like this, going up and down in a periodic way. Okay, so it will be a periodic, and V has to do the same thing. Now, you could ask, is this reasonable? Okay. And okay, I think I have a nice plot of solutions here with the hare and it's a fox, yeah. So you see that there are oscillations up and down of both populations. Okay. What else can we see from this thing? Is it's not like the usual oscillations that you would see, like a sinus or cosinus, okay, function. That's just, these are nonlinear oscillations because these equations are nonlinear. So for those people that have not studied differential equations, it's a linear and the nonlinear differential equations, but there's a formal definition. I don't give formal definitions here, but in practice is like I have on my right-hand side here, I have a product of V and P, okay? If I have products or have like a P squared or V to some also squared or whatever, then this system is nonlinear. Okay? So, and these are called nonlinear oscillations. It's not just a sinus. And then we can learn something else also here. So the maximum of the number of hairs of the prey, okay, is not synchronized with the maximum of the number of predators. Okay, they peak at different times. Okay, yeah. Okay, now that good. If you ask me in a formal way, okay, I would have to go back to the equations and see, because it's kind of error of time, yeah, problem. Okay, you can go in one way or other. Okay. The other way doesn't make sense actually, and I will come back to this in 5 minutes. So yeah, that's the way that works and has a biological meaning, because we want the predator to consume the prey and not the prey to consume the predator. It could be thought that, okay, never mind. So, now, the peaks are not synchronized, and we expect them not to be synchronized, because what is happening here is actually in a more biological way. What you have a certain number of predators and a certain number of prey. Say you get back to this curve with the point point 1 at the previous plot, and then you have a certain number of prey and predators, and they increase. The increase of number of predators comes from due to the fact that there's a lot of prey. Then the prey increases, then the predator increases. But if the predator increases a lot, what will happen is that the prey get depleted, will decrease. But if the prey decreases, the predator has no food, no prey, therefore it will die out, and so it will decrease. And once the predator decreases, the number of prey will increase because it's not being predated, and then everything starts again. Okay? And that's why you have to go in this direction, because you want the prey to increase first, and the prey increase first, and the predator after the prey. If you invert it, it would be like first you have a lot of predators, and then this creates a lot of prey. Okay, it would be nonsense from the biological point of view. So all of this makes sense, and as you have probably remarked, I didn't solve the equations. Okay? I didn't solve the equations, and I didn't show you any solution. But with this analysis, qualitative analysis, I can come to a conclusion. And what's the main conclusion? This is a more important thing now. If you go out in the field or in the lab, you see that there are populations that are not constant in time. It's not like single species dynamics, who are a little bit boring, that they only increase and saturate. Okay? There are populations in nature that actually oscillate, that change their number of individuals in an oscillatory way. Okay? There's been a long debate with what makes the population actually oscillate and so on. So there's a problem of saying, okay, now I'm going to look at the seed oscillations. So what's happening? What makes the population oscillate? Okay? So then there's one obvious reason that you could say. I have an oscillation, say, and the period of the oscillation is 1 year. What would you guess to be the mechanism? Seasons. Okay? Has nothing to do with predator-prey. Okay? Seasons. So an external factor. Okay? A completely external factor. If you have offs, you can have also day and night oscillations, and so this kind of thing, which is just the environment where the species lives is changing in time in a periodic way, and the species is responding kind of linearly to that. Okay? That's a way to have oscillations. What this result shows here, and this is important, is there are oscillations that can be explained not by the seasons, and therefore they don't have necessarily period 1 year or 1 day, or neither a multiple of this value. They can have any value of periods, and they are intrinsic to the dynamics of predator and prey couples, say 2 species dynamics, has a pattern of dynamical behavior which are oscillations. So this is the importance of the Lotka-Volterra equations. The main importance is it was the first time that somebody could show that oscillations in nature can be the product of interactions. That's the. And why I'm saying this is so important? Because, well, then you could say, yeah, you have equations, you have predictions. Can't we go out in the field, in the nature, and see if your equations are okay? Are they really predicting things? Okay? Then you say, oh, God, it's not so easy. First, because observations are difficult, but even if you had very good observations, the Lotka-Volterra equations is too simple to describe real situations. But we can build upon these equations to have more biological, meaningful mechanisms here and get more realistic things. But the importance is, and this is something that you should always remember when doing modeling, because many people say that modeling will give me predictions. So I'm working with some I don't know, some model of species here, and I'm modeling, I don't know, anything, amphibians and whatever, and I have a model. And then I want to make a prediction, exactly prediction. If I increase the habitat, I get this or that. But this is not the way that modeling in ecology, in particular in ecology, works usually. This is not like that. It's much more understanding the patterns. So you're understanding one pattern of behavior, of change, which is oscillatory change. So we are connecting interaction to oscillations. This is already something important. Now trying to say, given A, B, C, and D, then you could predict the period, and then going out in nature trying to see this period will not work. And then we will discuss this at in a moment. Okay? So, very good. Okay, is it true? Okay. So there are very important problems here. Okay? And one that I didn't put on the slides is the following. Now, usually when you go for observations, you will see that a certain, most of the observation of oscillatory dynamics like that are doing and come, the best data come from the very cold regions in northern Europe or northern Canada, because that's where you don't have so complex networks, okay, of interaction, so that you get easier observations and this kind of thing. But one thing that you observe is that there is usually a typical period of oscillations. And this period is the same if I'm, say, in the east coast or the west coast of Canada. Okay? Although there's thousands of kilometers of separation, they have the same period. Okay? So there's a typical period associated to a pair of species that interact in a predator-prey way. Okay? Now, this is in contradiction with the Lotka-Volterra model. Okay? Because the Lotka-Volterra model, and this goes back for the question that you made at the very beginning, has a problem with it's not a robust, I mean it's too robust actually, model, in the sense that, say that this is my idealized world, my ideal world, where you have two species and on the environment is supposed to be fixed. Nothing happens. But in practice, this is never the case. You have perturbations. So let's now think about a very simple perturbation. My system is, say, on this trajectory here. Right? And then there's a perturbation on a very short time scale that somehow shakes my system and takes it, say, here. Something happened, a hunter or disaster, catastrophe, something. It takes you here. And then, well, you are here, you are trapped here, okay? You go here, okay? This has a period, and this has a different period. Now, systems are under perturbation all the time. So they would go jumping and being trapped in some place with a certain period, which would end up being a non-periodic trajectory, because they are trapped always here, then you go here, you're here, then you go, say, here, then here, okay? You never go back to the trajectory you were at the beginning, okay? But this would say that there's no period associated, no intrinsic period associated with a pair of predator and prey species. The period depends on the initial condition. So this is in contradiction and say, in the west coast and the east coast, I have the same oscillations, but they are separated. Why would they have the same period? They would have to be exactly the same amount of predators and prey in order to have the same period. But this is not true. It's not true. So, problem, okay? These cycles exhibit okay, these are cycles. We are glad to have cycles, happy, wow, champagne. But, okay, these cycles are not realistic. Okay? What would be realistic? Would be, I'm on this cycle here, I get perturbed, I go back to it. I get perturbed, I go back. There's a certain amount of time to go back and so on. But so what would be realistic is to have a preferred cycle with a preferred period, which would be the intrinsic period of oscillations of this pair of prey and predators, and not something that depends on the initial condition. We don't care about the initial conditions. We want them to be erased, because we don't want this, because this is in dependence upon the initial condition. In this case, is something like opposite to what we see in nature. So what we want is to have a preferred cycle. We don't have preferred cycles here. No preferred periods. So this is a problem. It's the main problem with the Lotka Volterra. What we want is a preferred cycle, or what is called usually a limit cycle. Limit cycle is something on the like that. A certain preferred cycle such that if I'm here, I will approach and be near to the cycle, and if I'm here, I will spiral out or just go directly, whatever. But such that asymptotically in time, for large time, I will be near a preferred solution, the preferred cycle. This is what is called a limit cycle. And Lotka-Volterra equations do not have a limit cycle. They have cycles, but they are not limit cycles. Yeah.
Dynamics of whatever play and all the exterior variability.
No, I'm still considering, okay, what I'm considering in the models is always that there's no exterior variability. And I'm saying that if I have this kind of thing, and I have a perturbation, okay? A perturbation that after some time, it's over, okay? So that somehow takes, you are here, and then somehow this goes up here, because something happened. If this is a limit cycle, it will go back to this.
That's what I want to see that happens for
Yeah, okay. So we want a limit cycle is something that is like, you know, yesterday I talked about fixed points. Yeah. So the limit cycle is not a fixed point because it's not fixed. Okay. But if you are a mathematician, you can say it's a fixed point in a function space, okay? But anyhow, it's the parallel concept for cycles, like you have fixed points and you have limit cycles, okay? So this is the main point about the Lotka-Volterra. The problem with the Lotka-Volterra model is that it's not a limit cycle, and actually there's a very intuitive limit cycle in our lives. All of us know limit cycles. So I want you to think a little bit about your everyday life and give me an example of a limit cycle. Come on, people. It's now time for you to guess. Yeah, exactly. Oh, this is you should have waited a little bit. Yeah, your heart, because you have a certain heartbeat, okay, a certain frequency. Okay, means a period. Okay, you have a frequency, say 80, and then you get perturbed because I don't know, you get nervous or you just run a little bit. You get perturbed, and it goes back to 80. If you have a Lotka-Volterra heart, you have a problem. You get perturbed, you get up to 150, then you go and you rest. Or you take just a calm again and so on, but you continue with 150, right? So your heart has to be an oscillation, and it's a limit cycle. Okay? So there's a formal comment for people from physics. I don't expect biologists to know about that. But, this is what we call in physics a conservation law, okay? It's conservation law. And then you say conservation law, you said, this should be a Hamiltonian system, yes? Isn't there a Hamiltonian system? No, Lotka-Volterra is not a Hamiltonian system in this form. But actually, there's a change of variables which transforms this system into a Hamiltonian system, and the Hamiltonian is conserved, and this is typically a Hamiltonian system. Is this of interest? Well, it's a curiosity. Why? Because we now want to have better models, and the better models are not transformable to Hamiltonian systems, so there's no point of trying to introduce Hamiltonian formalism into these things. Yeah. Okay.
You just say that the problem with the Lotka-Volterra model is that we don't have a preferred cycle.
Yeah.
But in nature, we don't see. I don't know. I don't know so much of biology, but I think we don't have systems where we disturb them and then we don't come back to a preferred cycle. I don't know.
Yeah.
Or
Yeah. Sure. Yeah.
I think we don't have a preferred cycle.
No, not the. Okay, that's another point. The good point is that Lotka-Volterra gives you always cycles. The only thing there is between predator-prey is cycles. But not all predator-prey relations are cycles. There can be fixed points. There can be different things. Okay? Not necessarily cycles. Okay? And Lotka-Volterra predicts cycles always.
Also, if, for example, in Lotka-Volterra case, every cycle is equivalent. But if we those parameters like A, B, C, and D, they are time dependent, like some frequency because of season or environment. Then couldn't there be a resonance?
Good. Yeah, there could be. It's usually not studied in this. I don't know what the result for Lotka-Volterra actually is. But I know that for the next model, I will write down that there you can have resonances. Yeah, that's a very nice problem to study usually, having parametric resonances. Yeah. And actually, there's a tutorial on our wiki page after numerical integrations and so on, and in one of them, there is how to draw a resonance curve. Okay, numerical equation. Yeah. It has been done for the next model, not for this one. So now we want to have better models, and better models means we have to put more realistic biology into play. We are not playing the good game, We are saying things that is something, because you have to be rigorous. Your model has been built on some assumptions. Yes, these assumptions take you to this, and this is not correct. It's nice to have the cycles, but these cycles are not realistic. This has something to do with what? With non-realistic assumptions on when you build the model. And so, how can we now attack model? Let's go and attack the model. Then there is one thing that is obvious. Exponential growth of prey. Come on, nothing exponential in this world, okay? Therefore, simple modification would be, I let everything the same, and I will write just this equation will be modified. You will have some a v 1 minus v over k, and what is left there is minus b p times v. Okay? Just introduced saturation. And I leave the same equation here, because here there's no point of putting exponential growth, because there's no exponential growth, it's just a dash rate. Then you say, okay, nice, more realistic. What is the phase space portrait of this? And well, I give you the result. You have start here, and you spiral to a point. For large times, no oscillations. All oscillations decay. Oh, I lost my oscillations. Yeah? I lost my oscillations. I mean, I have, if you plot this on like this, solution, time, P, this is something like this. Okay? So you have oscillations, but they are of decreasing amplitude, and at the end of the day, you don't have any oscillation. It's the fixed point. You can find a fixed point for this system of equations. You can show that it's a stable fixed point. So, well, what a pity. We lost the oscillations. We want the oscillations back, yeah? We want the oscillations back, because actually we did like to have oscillations. But then you have to put some more realistic biology into the game, yeah? And what can we do? Oh, let's look what is happening here. Let's look at this term. V times BP, okay? Just at this. So the predator-prey equation, the prey is affected. Oh no, that's not a good one. No, I don't want. Yeah, this one. Okay. You have a term which gives you dv dt, blah blah blah, and then you have something which is minus b p times v. So, this is, what is this? This is the variation in the number of prey, okay? So that's the number of prey consumed by unit time, okay? That's the number of prey per unit time that is consumed by a predator, by a number, p predators. Let's think about p as being one predator, just p equals to 1, just to make things simple, okay? What this is saying is that the number of prey consumed by unit time, if p is 1, is just proportional to the number of prey. Okay? If I have more preys, then I will consume more preys. This is like I go to a restaurant, I've been given one sandwich, I consume it in, say, 10 minutes, but if somebody gives me 10 sandwiches, I will also consume the 10 sandwich in 10 minutes. I'm not satiated. I'm a super predator. If I get 1 million of prey, I consume them in the same time as I consume one of them. Okay, this is bad, yeah? Okay, the number of prey that are being consumed never saturates. But what you expect is to have a saturation. Okay? That at certain point, the predator cannot prey more than a certain amount of prey per unit time. So you'd like to have a modification of the Lotka-Volterra equation together with this assumption here, such that the prey, the predator, has satiation. In other words, satiation can also be thought that there's a time necessary to consume the prey. In this setting, it's like the consumption is instantaneous. Okay? So there's a handling time. So there's a time that the predator needs in order to actually consume the prey, and while consuming the prey, he is not predating others. Well, there is a way to find such a system. I won't do the demonstration because we are limited by time also. I don't want to go too long with this. But if you put, what you would like is to have something here that instead of having P, you had some function of V here, instead of having V, a function of V, such that, because what I had was, the function was just linear, like that, okay? Now I want something which is a function, f of v, in terms of v, okay, is a function that increases and then saturates. Should be the largest amount of prey that can be consumed by unit time. Okay? So I can actually kind of write down a simple expression that has this behavior, and then I will get to the system of equations, which will be like that. Minus b times p times v divided by oops, 1 plus b times some new constant h, v. Fraction. Okay? It's getting complicated from the point of view of solving the differential equations and so on. You have fractions. We don't like fractions. Physicists, when they see a fraction in an equation, they say, well, probably wrong. But no, it's not the case in this case. Then I will write this here. I will still assume that the predator is a specialist. But you see, this is the same term here was b times v, just with a different constant. Here was b and here is c. So this is kind of conversion rate, okay? B is not equal to c because it's not like I eat one fish and I generate one offspring from each element of the, there's a conversion rate, okay? But this means that I should also modify this here. So you will get C, where is the, times times some C times B times P, 1 plus B dash P. So this system of equations plus is called Rosenzweig McCarter equations model. Okay. So now you have a new constant here, and this is called the handling time. You can show if you go and do a dimensional analysis, okay? You want to determine the dimension of your constants. We have not talked about this here. All these constants have dimensions. And the dimensions of this guy here is time. Okay? In order to have all the terms have to have the same dimension, in order to have the same dimension here, this this new constant has dimensions of time. Okay? Yeah. Hmm? Well, the new constant, there's the mechanistic demonstration of this. That's what I wanted to avoid because it's lengthy. What I'm saying here is, well, I want to have a function that somehow will saturate, okay? I want to saturation. So something has to determine the level of saturation here. Okay, so you need a constant connected to this. Okay? Yeah. So this is the constant here. Okay? But well, then if you make if you look, what's the dimension? It's a dimension of time. Okay? So it gets the name handling time, and it's possible to show in a mechanistic reasoning is like consider the time spent by the predator searching and handling. And if you separate this and so on, you can demonstrate, you get this formula. If you are interested in this, you look at the book of Gotelli. Okay. Oh, yeah, sure. Thank you. So this is the Rosenzweig-Mercator system of equations, and now we have equations, we want solutions, okay? Again, no analytical solutions, all the story. I will just show you the phase space portrait, okay? Phase space portrait of this guy is interesting. There are two patterns, and depends on the combination of constants, but can be taught as dependent on k. For large k, no, if it's large, it's like there's nothing. Yeah, for large k, you get limit cycles. You get a limit cycle for large k. A small k, fixed point. Depending on the value of k. But I mean, it's not just the value of k in absolute terms, it's the relation of k with the other ones, okay? So there's a intermediate value of k, which I will call k critical, which separates the solutions that are limit cycles to the solutions that are fixed points. Yep, exactly. And for large k, oscillations. Okay. So we're back to oscillations, but not always. And this is good, actually. We have two different situations. You can have fixed points and we have the cycles. And the cycles are limit cycles. Oh, okay, this is much better, much better a model than the Lotka-Volterra equation. Okay? Is it perfect? No, it's not perfect. But it has much more realistic assumptions and realistic results. It is, I don't have it in my mind. The K is related to the combination of B, H, C, D, and A. I didn't calculate actually. I have this in other units here. No, the K will be a certain value of K, which is a function of all the others A, B, C, D, and H. You give you a fixed certain value of K. Below this value, you have fixed points. Above, you have and actually the period and the size here of the limit cycle depend on K. Okay? If you pay attention today at the evening session, Roberto will show you this example, and this is what people call a bifurcation. You have a certain time of solution, which is, say, fixed point. You increase one of the parameters, say K, and after a certain, and you get always a fixed point, not the same value of the fixed point, but get a fixed point, and after that, you get a cycle. So you bifurcate from one qualitative kind of solution, which is fixed point, you bifurcate it to cycles. Okay, so it's a bifurcation. So very nice. So all of this is not on the slides. Okay. But, you know, I like to talk about the glories and miseries of each model. So the glory of the Lotka-Volterra model is it gives cycles. The misery is these are not limit cycles. It cannot be realistic. Glory of the Rosenzweig-McArthur are many glories. Okay? One of them is it has limit cycles and fixed points, and this means you have possible different qualitative scenarios, which is what you see actually in the nature. It is much more realistic. But now every model has a misery, right? And there's one point here. Now let's look for large K. What does it mean, large K? Okay, K is the carrying capacity for the prey. Okay, that's it. I mean, large K is, well, it's kind of, there is a high, the environment is rich. Okay, there's a lot of nutrients. There's space, nutrients, and in the absence of the predator, you can have a lot of prey. So it's a rich environment. It's a kind of richness measure of the environment in relation to the prey. Okay? Rich environment, you have more prey. Now, this is saying that the larger case will give you oscillations. But now say you have a large K, but you still want a larger one. Okay? Well, you still get oscillations. Always oscillations, but as you increase K, you get back to this kind of thing here. These are the limit cycles. This is not anymore the same thing as the Lotka-Volterra. Each of them is a limit cycle because it's not for different initial conditions, it's for different K. Okay? So don't mix up the two things. Okay? The diagrams look alike, but it's not the same. Yeah? This is for different parameters, not different initial conditions. So the larger case means high productivity or richness of the environment. You get larger and larger cycles. But this is awkward because, you know, these cycles are large. They never get to negative values, but they can get very close to zero here and here. The richer the environment, more likely you can have a crash of the population because the oscillation goes up and down and gets very close to zero, which would be, well, let's call it a biological zero, okay? Because a certain amount, but if the very small populations, we are describing populations by continuous functions here, but actually, well, the population of 10 to minus 3 individuals is a zero population, actually. Yeah. So rich environment should make the population crash, and the richer the environment, the more likely you are to have extinction of the prey and of the predator. System crashes, the richer environment. So this is against intuition, but no, intuition can be wrong also, okay? But it's called the paradox of enrichment. Okay? It's actually not a paradox, yeah? Okay? There are some, in ecology, people sometimes like to say that there's a paradox of plankton, there's a paradox of enrichment, and these things are usually not paradoxes in the logical sense of what is a paradox. It's just a non-intuitive thing, okay? Maybe sometimes people say that it's a paradox, but it just means that your model is wrong. Okay, it's not a paradox. Okay? So, but anyhow, then you can say, okay, but wait a minute, can't we go to the lab and see these things? Yes, we can go, and you see that oscillations can be of larger amplitude when you have more rich environment, okay? But now you expect that in nature, well, something else should happen. If I have oscillations and enrich the environment, you don't expect these things to collapse, okay? So that's the possible critique of the Rosenzweig-McArdle model. And well, it's not something that is really a paradox, but it's something to take care with interpretations here when you go for large K and so on. Maybe there's some other biological factors. Maybe you should take more realistic biological assumptions. It can be of maybe there's important variations in the environment. Maybe you have to have more species, whatever. And that's it. Very good. So what's the yeah? No, there's no paradox. I mean, there's a fixed point, and because it's like a little bit. This is in K is small. It's like the oscillations are kind of, there would be an oscillation, but the K is limiting the oscillation, so it's damping. Okay? Can be other ones, yeah, sure. Yeah, it's true. I'm simplifying the discussion because actually what you have here is you can think of a critical K, but you can think of there's a relation between the parameters, such if the relation is certain combination of the parameters is smaller than a certain value or larger than a certain value, you have one case and the other case. That could be also modifying A, B, V, and so on. Okay. It's usually called the paradox of enrichment because it has been presented as a paradox of look at K and see what happens. Okay. The stable coexistence of predator and prey. Stable coexistence of predator and prey. They are in equilibrium here, in this case. Yeah, but then now you're coming in with like metapopulation things, and data population has different assumptions because the probability of extinction it's kind of you need well, I mean it's completely different, but the extinctions are not, they are really random. Okay? And
But you use it applied from which environment?
maybe, no, I never thought about this problem in this context. Okay? But, well, anyhow. So, it's a critique, but it's not like the model is wrong, we have to modify everything. It's not this. Okay? If there's something in predator-prey theory, which you could call it the standard model, okay? The standard model would be the Rosenzweig-Mercator, okay? It has sufficient realism and on the biological side, and still is simple. This is, even if you think it's complicated, it's actually simple. Okay? It can be much more complicated. For instance, what else could you take into account? Okay? You could also say, now, here, if there are many predators, they will start to interfere. Okay? I didn't take this into account. Here, the predators don't interfere. If I have one predator, it will be able to consume a certain number of prey per unit time. If I have two, this guy doesn't care about the other. Okay? But if you have a small number of prey and a large amount of predators, this will not be true anymore. There will be a kind of competition for the food, so there will be interference of predators, and this should modify your equation. And actually, the modification that will appear would be something plus a new constant, b times, I don't know, something. Call it gamma, okay? P, okay? Plus b gamma p. This would be the result if you take into account interference of predators. It's called the Beddington-De Angelis model. Okay. Well, so at the end of this, what's the take-home message? The take-home message is you have a way to build the models from predator-prey. If you put two simple assumptions, what will happen is that you get results that are not consistent with what you see in nature. But if you increase the realism of your biological assumptions, you get new models, and you can have a kind of systematic way of building these new models, which gives you more realistic results on this. Other take-home messages: predator-prey equations are predator-prey relations are ways to have oscillations. Okay, they can generate oscillations. And with the Rosenzweig-Mercator model, we understand that there will not be always oscillations. We can have fixed point and oscillations. It's not like Volterra. Okay? So, there's a lot of literature about the nature of predation. There are different models. There was a famous dispute some years ago about this kind of model, or models that depend on the ratio of the number of prey to predators, that depend on V over P as the essential variable. It's called ratio-dependent models. There are people that, in particular, a guy called Burke from Stony Brook, who is kind of promotes this idea that this is a better way of looking at predator-prey equations. But still, the mainstream think like that. Very good. So that's all for the lecture today. Do you have a question? Yeah, sure.
Have we some fits of this model to?
No, I don't think you have fits. What you have is people do something else. People do. You see this here, like. This part of the equation here, this f of e, that's called, okay, this has a name. That's called a functional response, right? That's the number of prey consumed by unit That's the function here. This is called the functional response, which is connected to the number of prey that can be consumed by one predator per unit time. Okay? So this you can actually assess experimentally in many systems. So you have papers on functional responses, and a lot of people, because this is a concept that lives without the equation also. I mean, how many preys can you consume? So there are hundreds of functional responses out there, being experimentally determined or observationally determined. But usually this kind of fitting these things is difficult, because if you want to go for the field observations, it's obviously that there are more species, environment is changing, and the cycles that usually you'd have here is if you're talking about big species, mammals, you talk of cycles of years. And actually, say like 4 years, but in 4 years, the chances are that the environment will change, that there will be too many perturbations that you actually cannot get a real fit for that. Okay. Yeah, there are actually people from USP, Paulo. You're working with Renato on predator prey with bacteria, or what was it, competition with the lab of your friend there? Ah, okay. Ah, it's competition. Competition. Okay. Okay. Ah, okay. Ah, yeah, it's competition experiments. Okay, it's not the predator prey. But I guess you can have small microorganism predator prey dynamics, and I don't know, bacteria or protozoa. Yeah, you can have this. Yeah, maybe you can try to see if the equations fit in this case. I'm not aware of these results, actually. You could say.
Actually, it's a classical experimental setting to test some hypotheses about
yeah?
tons of papers.
Ah, okay. And I'm not aware of the tons of papers. Yeah. So there was a question here. Oh, this is and it's a complicated starting point. Actually, the integral predation, well, you have 3 species. What's integral predation, people? It's like you have two competitors, two species that feed on some resources. Okay, so you have a resource and you have 2 consumers. Okay, so they are competing. Okay. But one of the competitors is able to prey upon the other competitor. So you say when two consumers feed on the same resource, then they are guild. And intra-guild predation is when you have predation between them. It's common in systems like mites. Yes. And yes, but I mean, you can go handling time in this case is not used. The basic paper of Polis and forgot the name. It's much simpler. Okay, it's without this here, without this part. 3 species, and that's it. Okay. Yeah. I don't think so, because actually the paradox is not so much a paradox. Maybe you have situations where you crash, actually. Okay? I'm arguing that this is strange, but I mean, strange things happen sometimes. Okay? why is it unresolved problem? Why is it still a debate on that? Okay, because what I was telling to him, it's difficult with field observations to parameterize equations and this kind of situation. It's difficult because, well, you are talking about cycles of years and years, and all the assumptions about the environment being constant, not being important, blah blah blah, are not true. Okay, so there's a problem with that. So I don't know. I'm not aware of the tons of papers that Paul told us about the predator-prey with microorganisms. Maybe there's some answer to your questions there. I don't know. Okay. Any other questions? Okay. So today you go for your group work, and what do we expect, more or less, just to give you some guidelines, okay? We expect that today you have the questions, you have the elements of the model. Even if you're not sure about equations, you should now more or less say, okay, what will go into the model? What effects will I take as important? What will I just disregard, saying this is not important? So the elements which will go into the model, what's the general approach to the modeling procedure, maybe some equations, but okay, if you still are not sure about equations, and so it's the moment to get, you know, the problem, you will have some objective, some questions that you want to answer with your model, and you should now start, okay, what goes into the model and what stays out of the model, okay? More or less this. And if you say it's, I don't know, 3 o'clock, we have everything, let's start with equations. Well, we'll have equations, okay? But be sure that one thing is, do not start writing down equations if you're not sure of the elements of your model, because it will be a waste of time, okay? So, thank you, and at 6 o'clock, we have the evening lecture today.